So John comes to us from the University of Minnesota, where he's the director of the Institute on the Environment and runs a group on the Global Landscapes Initiative. For me, it's a particular pleasure to have John here because back in the day, he was my master's thesis advisor when we were both at the University of Wisconsin. And it's been really exciting for me to have him here over the last few days in Lund and here in Stockholm to hear the innovative work he's been doing. He'll be focusing on a new paper that came out in Nature, I think it was last week, called Solutions for a Cultivated Planet, talking about real-world solutions for this very important problem of food security, how it is that we can actually best achieve food security and feed the 9 billion people that we're expecting on this planet now that we've passed the 7 billion mark just in the last week. So we really look forward to hearing what John has to say and time for discussion afterwards, and very happy to have him here. So please join me in welcoming John. Thanks.
Thank you. Is it on? Oh, very good. See if my computer speaks Swedish. Ah, good. It does. All right. Well, again, thank you very, very much for having me here today, and thanks to Kim and colleagues for the invitation to come to Sweden for the week. And it's been very, very exciting, actually, to see a lot of colleagues and a lot of old friends. So thanks very much for having me here today. So I was asked to give kind of an overview presentation about this challenge of global food security. And I'll be talking about different kinds of results in this. But I think we're going to be starting basically from this kind of perspective, maybe starting from this global top-down point of view. And what I find very exciting about the program today is how we'll be kind of talking about a number of issues and then getting more and more specific as the day goes on into different regional studies. So it's a very exciting day. But to start maybe with this kind of overview, I think it's useful to think that agriculture today faces basically three very big challenges. Many, many more too, but there are three that everyone would find, I think, very universal. First of which, of course, is the question of contemporary food security. How are we doing today? And this is a huge issue, as just in the last few days, the world passed the 7 billion mark in terms of population. And it's estimated that roughly about 1 billion people in the world today are currently malnourished or chronically food insecure. That's quite alarming in that in only 3 years, that number has dramatically increased. About in 2008 or so, it was only 700 million, and now it has climbed to roughly 1 billion in just 3 years. Actually, it almost all happened in 1 year, around 2008. So there's some very large concerns about this issue of, can we feed today's world? That alone is something that is an issue mainly of institutions, economics, and governance, but which are really, really important. But as we move into the future, whether we even have enough food at all, even if it were distributed equally and properly and equitably, is a real question, because there are huge demands in the food system that will be increasing as we move into the future. So one issue, of course, is continued population growth. We're at 7 billion today. We'll at least hit 8.5 to 9 billion at a minimum, just due to demographic inertia in the population structure of the world, but that it could also go beyond 9 billion, perhaps to 9.5, perhaps even 10 billion, if you believe the latest UN forecast. So population growth is certainly an issue from 7 to 9 or 10 billion, with 2 to 3 billion people on the way. But even more importantly, which is quite interesting, what will drive food demand in the future much more than population itself will be our changing diet. Much of the world, China, India, other countries, are rapidly developing their economies and their standard of living. And in doing so, they're adopting some of our bad habits in the West. By eating maybe more protein, meat-based diets or more high-calorie diets, things like this, which are much, much more resource-intensive than just a simple plant-based diet. So yes, population will be driving part of the future demand, but more of it will be coming from changing diets, if things continue as they have in the last 2 decades. Taken together, without even thinking about biofuels very much, even without that, just changing diets, followed by changing numbers of people in population, shows that we probably are on a trajectory where, if things continue as they are today, we would be heading towards a rough doubling of global food demand by 2050. And interestingly, it would not stabilize. Even if population numbers were to stabilize, food demand would continue to increase as more and more people become more westernized in terms of their diets. So it's 2 times, and it will keep growing. So that's huge. And I mean, just think about this too. Agriculture is roughly 9,000 years old, 10,000 years old. It took us 9,000 to 10,000 years to get the food system we have today. And we have to double its throughput in the next 39 years if things are going to go as projected. That's a very, very big change. And we'll get to that in a minute. Finally, of interest to a lot of people here, of course, is the environmental impact of agriculture and the requirement to make it truly sustainable. Not just sustainable with a label on it and pretend that it's sustainable, but truly environmentally sustainable is something that we have to consider as well. And this is an enormous challenge because agriculture is such a large human enterprise, and I would argue is the single biggest environmental issue on the planet. Much bigger than energy use, probably bigger than climate change, and it's huge. It does everything. And let me back up that kind of bold statement, because I'm a climatologist. For me to say that agriculture may be a bigger issue than our traditional views of climate change, I need to back that up a little bit. So let's first show some data. First, for example, is just the extent of agriculture, the physical extent. First of all, it's just incredible how much of the world's real estate, its land surface, if you will, is consumed by agriculture. All of the green areas in the world are devoted to cropland. That's about 16 million square kilometers, or about the size of South America, to put that in perspective. The world's rangelands and pastures are about 30 to 34 million square kilometers, depending which numbers you believe. That's all the brown area on the planet, and that's roughly the size of Africa, to put it in perspective. You take those two together, agriculture has already basically fundamentally disturbed, changed, and remodeled 40% of the Earth's land surface. That's a bigger reorganization of the biosphere than we expect even with a doubling of CO2. So this is huge. And you look at then, where would we feed the next 2 to 3 billion people? How will we double the world's food supply when most of the world's cultivable lands are already used? I'll get to that in a minute, but we are using the entire planet, basically, to grow our food. We also use an enormous amount of water to do agriculture. It's by far the biggest use of water on the planet. This is a picture flying into Phoenix, Arizona in the United States, looking at irrigated lettuce from a desert in Arizona, which is quite strange. And we find that water basically is a huge issue in agriculture. Oops, sorry, got ahead of myself here. This clicker's a little sticky. My apologies. What we find here is that the withdrawal of water out of natural systems from lakes and rivers and groundwater and so on is responsible for about 70% of that is caused by irrigation. When we think about the consumptive use of water, that is water we take out of nature and it doesn't go back to the same watershed, it evaporates or transpires into the atmosphere, it's roughly 80 to 90% of global water consumption is used for agriculture. So again, much bigger than any other human enterprise and already represents a considerable modification of the world's water cycle. And then, of course, is also the single biggest, agriculture is the single biggest source of water pollution in the world as well. Not because it's necessarily dirtier than industry or anything like that, it's just so large. The huge volumes of water and land that are involved, and especially in terms of nitrogen and phosphate pollution, agriculture, once again, is the biggest thing we've done to the planet. So we look at the land use, the water use, and getting back to climate change, ironically, agriculture is once again the biggest kind of dominant force in thinking about climate change. At least 35% of our greenhouse gas emissions can be directly attributed to agriculture. That includes some of the big things you would expect, like deforestation. It includes methane from rice and cattle. It includes soil nitrous oxide. What it doesn't include is the energy used in agriculture itself, which, depending on the estimates, might be an additional 5 to 10% more greenhouse gas emissions. So at least 40 to 45%, when you put it all together, of greenhouse gas emissions are due to agriculture. By comparison, all of the world's transportation is something like 15 to 18%. All of the world's electricity is roughly 15%. All of the world's manufacturing is maybe 17%. So again, feeding the world is by far the biggest thing we're doing to the climate system as well. So this is a huge challenge, getting back to this larger global perspective. And it's a triple challenge where all of these three things are interwoven. The need to address food security today, the need to double, perhaps, the world's food supplies into the future if we hope to meet the current increasing demand trajectories for population and diet, let alone biofuels, and make agriculture sustainable. That's a very challenging list right there, of course. All of those are bigger challenges than we've ever really dealt with before in some of these things. And the problem is we have to solve them all at the same time, which is going to make things incredibly difficult. So we, an international group of us, including people from Sweden, from Germany, Canada, and the United States, we decided to try to tackle this issue in a very preliminary way, very, very preliminary in many ways. But we decided to look at this issue of how could you double the world's food security and food production, that is, while simultaneously dealing with these environmental issues. Usually in the literature they've been dealt with separately. We decided they needed to be dealt with together. So we just had a paper come out. It was in Nature just, I don't know, 2 weeks ago or something like this. So you should be able to find it if you hadn't seen it. But it's, we called it Solutions for a Cultivated Planet. And the solutions really were to look, again, at environment and food security together. But in order to do that, we really had to do some new science. A lot of these things were done in separate silos, and we wanted to bring them all together. So first, being scientists, we decided we needed some data. We wanted to get good global data. And the good global data we have in the world today might be from satellites. We can track agricultural extent and area and things like that using satellite imagery. We can look at how farms all over the world differ in terms of their geometric configuration, their amount of area, all that kind of thing. And that's quite fancy, and everybody likes these kinds of pictures, and that's nice. But it's very, very hard to tell, except through human intuition, what's happening on the ground here. You and I can tell, oh, those must be rice terraces in Thailand, and these are probably soybeans in Brazil. But it's very hard to understand farming systems by measuring the reflected light of chlorophyll from outer space, which is what this really is. So maybe it could be more helpful to do some social science data collection where people go on the ground and talk to people. So every country in the world has agricultural censuses regularly where people are being interviewed and being asked questions about what did you grow and how much did you grow this year, what was your yield, who did you sell it to, and so on. So our team collected kind of census data for not just individual countries, but for individual states and provinces and even districts and counties all over the world. Every polygon, every little shape you see on this map represents a single political unit that we're tracking with these social data at our university and with some colleagues. It's about 25,000 different political states that can be tracked with census data today, probably more. Well, we developed techniques that, and I won't get into this today, but that basically fuse the data between remote sensing and satellite imagery and the social science data, bringing together the best of both worlds. And this allows us for the first time to have truly global data that describe the extent of human actions, including economics, around things like food and fertilizers and land use. So some simple things we can do is like track, well, what fraction of the world grows maize? So this is a map of the world's maize production, where it is, what areas are being used. But maybe more importantly, and I'll show this a lot more later, what is its productivity? Why is it highly productive here but not so much there or there? We'll talk more about this later, and Nathan Mueller will be showing some more data like this in a few minutes. We can look at other crops like wheat and its area and yield and so on. And we got kind of obsessed with this, actually. We probably went a little bit overboard. And we decided to track not just a few crops, but about, well, now 180, I think it is, that we're tracking. And we're going backward in time. We're going back to the 1960s through today to try to have a single comprehensive data sets of what happened to agriculture through the entire Green Revolution transformation and beyond. But it's not just the agricultural land and productivity. Nathan, who will show this more later, developed some rather nice data sets that he'll explain in a little bit about management as well. Looking at, for example, how much fertilizer is being used around the world, both chemical and manure form, for example. We can try to track that. So here's nitrogen. We can look at phosphorus, for example, or potassium or potash, and looking at how we humans deliver nutrients. Stefan Siebert and colleagues in Germany have done a really great job also with exactly the same data grid and is exactly compatible with our data, which is a very nice collaboration with the German teams, have created these so-called Mirka 2000 data sets and subsequent versions looking at irrigation as well. So I think today we have a much better understanding of agriculture just from the data side of the planet than we did even 2 years ago. Really big improvements in this very, very recently, which is a nice thing for Earth system science. But the data alone aren't always that helpful. We also needed a conceptual framework within which to interpret these data and to think about them more or less from like a modeling or conceptual framework. So this conceptual framework that we used was basically to balance the issues of food security and the environment. What this figure is supposed to illustrate is that food security has many different dimensions. We illustrate just 4 of them here, but there are many, many more that are very nuanced. But the basics include, the production of agricultural commodities, the making sure that those commodities in fact deliver nutrition and calories, that they're actually food, not just commodities, that people can get them, that it's accessible, affordable, and there are distribution networks to do so. And increasingly, we're concerned about the resilience of food systems to things like disease, climate variations, price fluctuations, which are probably the most important right now. So this is all the goals we might have for food security. On the environment, we might think about kind of global planetary boundaries kinds of issues, things like greenhouse gas emissions, the loss of biodiversity, the withdrawal of water in unsustainable practices, and water pollution, especially nitrogen and phosphorus, at a large scale. The circle represents basically what do we need to be doing by the year 2050, kind of a scenario for the future. Well, this is where we are today. We do not meet any of these criteria for future or even current food security. We're falling very short of what we will need to do to feed the world. And on the environmental boundaries side of things, we've blown past all of them very significantly. We are emitting far too much greenhouse gases from agriculture, far too much biodiversity loss and water pollution and water withdrawals. This is not a picture of a future that we want. This is a completely unsustainable future where we fail the world and we destroy a planet. This is not a good thing. We do not want that. So what we want is a world where we do meet the needs of humans and we do so within the planetary boundaries. And so this is the picture of agriculture we want into the future. So in very simple terms, we want more food and less harm. And that would be our equation for sustainability in this case. So, well, first, before we look into the distant future and what can we do there, how are we doing today? What kind of trajectory are we on right now, just in terms of meeting food demands? Well, it's interesting. If we go back to our maps of agriculture and ask, where is farming going? Is it increasing in area and so on? We know, for example, that agriculture is moving into the Amazon here through the arc of deforestation. We know here over in Indonesia and Kalimantan especially, there's a lot of deforestation as well. But interestingly, the total extent of agriculture has remained basically constant. In the last 20 years, the total amount of cropland has only increased by about 2.5%. While deforestation is a huge issue, and we'll talk about that in a minute, the total amount of acreage or land base is still about the same. We're gaining land in the tropics by clearing forests mostly, but we're losing some land in the mid-latitudes, particularly in China, but also a bit in Europe and the United States due to urbanization. Not very much, but enough to notice. So there's not that much more farmland. What's really been happening is really the yields are increasing, or have been increasing. So for example, this is looking at the yield trends in 2 major crops, rice and maize. We did this for many crops. But this is looking at these 2 in particular, and we're seeing dramatic improvements in yield for rice, for example, throughout Southeast Asia, even the Americas. Also maize, we can zoom into and look at this a little bit more, seeing tremendous boons in maize yields. But these yields are not going up linearly or even exponentially. A lot of them are beginning to plateau, especially rice and wheat, the two most important crops in the world. The yields are beginning to slow down and in some cases have completely plateaued. That is very, very, very disturbing. So we have to really track, what's happening here in terms of the yields and whether or not we can guarantee future improvements in food delivery by increasing yields, or is it increasing area? Well, we looked at this in a lot of detail, and I won't go through this this was a bit inspired by Hans Rosling and his Gapminder kind of show, so I won't do the animated version, which he does so much better. But you can see here what we looked at is in the vertical axis is in the last 20 years, what happened to yield? 1 would mean no change, 1.2 means a 20% increase, and so on. In the the horizontal axis, we're looking at changes in the harvested area. That is, area that actually was harvested with crops. Anywhere to the right of that curve means we've increased the amount of food that was produced on the planet, either by increasing area, like we have much more sunflower seeds in the world today than we did 20 years ago for some strange reason, or maybe increasing yields like wheat. There's a little bit less wheat area, but its yields have gone up. Or, I don't know why, but we have a lot more garlic in the world today. That's pretty interesting. Must be all the spicy food we like today. I don't know. This is kind of fun. Cucumbers, I guess we've tripled the number of cucumbers in the world. So this is kind of fun. But what we've noticed, though, is that a lot of people forget this, but we've been losing crops as well. We've been losing barley, sorghum, and especially oats. Oats, we're only growing about half the land area of oats that we used to do, especially in Europe and the United States. So this is kind of an interesting thing. Small grains are disappearing, high-value things are moving out this way. So these together show us that actually, despite what a lot of agronomists have been telling us, I've always been hearing that, oh, we've increased the food production in the last 20 years by 45%. No, that's actually not true. That's only 45% if you look at the top 5 cereals. If you look at all of the crops, total food production only increased 28%. Actually, much less than you would think. A little bit more farmland contributed to this. We had 7%, though, more harvested land. Even though the amount of farmland didn't change very much, the amount that was harvested every year increased quite a lot. Partly because we had fewer crop failures and crop fallow periods, but also we had more and more land that was double and triple cropped, especially in the tropics. And yields, I'd always heard that yields had increased about 40% in the last 20 years. That is actually not true. That's only if you look at a handful of crops. But all of them, weighted by their production, only increased 20%. This keeps me up at night. This is a real problem because you can do the math. 20%, 28% in total increase in production in the last 20 years is not going to guarantee a 100% increase in the next 39 years. That math doesn't add up. So if we're going to be trying to keep pace with the projected demands, we are nowhere near what is necessary to feed the future if we continue to grow the way we are today. So if we want to meet the needs of the future, we have to accelerate our efforts and think very, very hard about how we will meet future food demands while also dealing with these environmental damages that we're so concerned about. So in the paper that we wrote that was just came out in Nature, we basically made 5 major recommendations about how could we do this? How can we double the world's food production, or at least the delivery of calories, not necessarily production, but delivery, and also cut in half, at least, the environmental impacts of agriculture, even more so when it comes to things like greenhouse gases. So that's what we set out to do, and we came up with 5 steps which we believe provide at least a framework within which we can maybe address this kind of challenge. So first is, ironically, is to stop expanding the land devoted to agriculture. That yes, we can expand agriculture into the tropics. This is a map showing where our croplands are today. This is where we estimate they could grow into and still be quite productive in terms of soil conditions and climate and topography with today's climate. But the problem is, most of the areas that we could expand into are in tropical forest or tropical savannas, places of tremendous ecological benefit of providing ecosystem services, those huge harbors of biodiversity, major reservoirs of carbon. So yes, we could expand agriculture, but at tremendous ecological cost. And it turns out most of the places that are being deforested, in large-scale ways anyway, are not contributing to real-world food security on the planet. For example, in Brazil, we're seeing a lot of expansion for soybeans and beef, cattle, but incredibly low stocking densities for cattle that aren't really feeding very many people. And the soybeans are mostly animal feed being shipped to China and Europe. So that's not really necessary for rural food security in developing countries. Same with oil palm in Indonesia. It's mainly a cooking oil for China. It's not really providing kind of local, real-world food security. So we looked at this as sort of a trade-off between what do we grow. This is looking at the kind of total yield of crops around the world and what their relative productivity is. The darker the green, the higher the productivity. For the most part, you notice in the tropics, except oil palm and sugarcane, most tropical crops are not very productive in terms of total yield, but they're extremely important to people on the ground. Here, though, we look at the amount of carbon that is cleared when you add another hectare of forest into cropland, for example. So the darker the color here means more carbon is cleared to produce one more arable acre or hectare. So here's kind of the trade-off map here, where we look at how much carbon was cleared per hectare to produce a unit yield. So the darker the red areas means there's much more carbon emitted relative to the yield productivity of that landscape. So if you were to try to expand agriculture, the last place you'd want to do it is in the red places on Earth. That would be the worst possible places to grow additional food by expanding our land base. And yet that's exactly where we're doing it. So this is a really big problem. So we pointed out that, I think it's not too surprising though, but if for climate stabilization, far easier than dealing with the energy challenges of the world would be dealing with deforestation. Again, this is maybe 18% of total greenhouse gas emissions. Cutting that in half, which I think is entirely possible, would be like taking half of the cars off this planet, which is be much harder to do. So this is, relatively speaking, more tractable, more doable, and we can really target particular regions through things like RED and other kinds of investment mechanisms possibly to curtail deforestation and have a dramatic climate change impact. So if we don't have more hectares of land to grow food on for the future, we have to grow more food somehow on the land we already have. And that gets to the idea of closing what are called yield gaps. Yields of farms around the world range from the very best farmers in the world, like those in the Netherlands or Iowa, and the very worst farmers in terms of yield, the least productive farms we see in much of the world. So there's a huge range of farming yield performance, if you only cared about yields, from the high to the low. But all of the money goes up here. This is where Syngenta and Monsanto and a lot of private research dollars are going into the farms up here. This is where genetically modified crops go. This is where high-tech agriculture goes, where subsidies go. This is where all the money is. But this is where all the land is down here. So there's a lot of land down here that's not very productive that could be raised to be medium production or maybe higher production and could be far more effective in delivering food, especially to people who need it, than trying to eke out a little bit more productivity up here using incredibly sophisticated and possibly dangerous technology. So why don't we worry about, instead of the yield ceiling, why don't we raise the yield floor and bring it up? So that's the yield gap. Nathan will talk more about this probably later today too, but we looked at the yield gap very quantitatively and said, well, for example, here's the Maize Yield Map, showing how maize yield varies from about 1 ton per hectare of maize, well over 12 in places like France, the Netherlands, the Midwestern United States, some parts of China. So there's huge variations in yield. This has actually relatively little to do with climate and not that much to do with soils, strangely enough. Soils are important, of course, climate's important, but what determined this map more than anything else statistically was management. That was the overriding factor, more important than climate, more important than soils. And so when you basically take soils and climate out of the equation statistically, we decompose that map, and I think Nathan will talk about this in more detail. We basically separated the effects of climate and management and soils out of this and came up with a kind of normalized map saying what percent of the potential yield are we getting today for your location. So it adjusts for changes in climate and soils around the world. So this map shows relative to every pixel on the map, between 0 and 100%, what fraction of the yield are you getting that could be attained in your location? When we look at this, of course, we see things that jump out at us. The green places are all very high. That's 80 to 100% of your potential yield. But there are a lot of places that are kind of in the red colors. We can look at southern Africa, for example, with the exception of Malawi, which is increasing yield dramatically. We see a lot of places that are not attaining yield that they could be. And I'm sure we'll hear more about this in the afternoon. West Africa, for different reasons, we see what's going on there. Mexico is very, very interesting because you see pockets of green next to pockets of red and almost nothing in the middle. You have very kind of advanced industrialized agriculture for maize, using high-tech seeds, using more inputs and so on, very much more like a European or American farmer, next to kind of peasant farmers collectively on land with open pollinated seeds that they kept for a few generations, that are maybe a factor of 10 difference in yield, right next to each other. A place that people often forget, though, is Eastern Europe. This may be the single best place in the world to boost global food production. Some of the most fertile lands on Earth, the kind of Central Eurasian kind of soils here. This was a breadbasket of the world until it moved to Western Europe. Now the breadbasket of Eurasia is between Frankfurt and Brussels. But if you look at Ukraine, Russia, Romania, this whole region, it's only getting about 20% of its possible productivity today. During the Soviet era, it was maybe closer to 40 or 50%. Soviet agriculture was notoriously bad, and now it's a lot worse. So the failure of institutions, governance, land tenure, and just getting the agriculture productive in this region. The soils and climate are totally capable of it, but they're not being realized today. So these areas become maybe opportunities for either some kind of intensification, hopefully a more sustainable approach, and something that could be done very, very interestingly. So we looked at this again. Nathan will probably tell us a bit more about this too, but we also asked, what was the thing that was limiting yield in these places? We asked if we wanted to boost the yields by 50%, what do you need to do? Well, in many places like Western Europe and the United States, you're already at the maximum yields. You're getting the maximum yields that plants are capable of today. So if you want to increase yields, you have to lift the yield ceiling. And right now, our approach to do that is basically advanced genetics, maybe GMOs. So that's possible, not always desirable, but it might be possible. But in basically everywhere else in the world, you don't need to play with genetics that much. Sure, some orphan crops need help, but for most crops, we already have the seeds we would need in Africa. They don't need GMOs. They need fertilizer. They need manure. They need water. Very simple kind of medium technology things could make a huge difference. So, rather than trying to export the solution that works best for Nebraska to East Africa, we need a different solution in each place. So I think we can tailor these solutions where we can have a much more kind of sustainable approach to intensification rather than exporting kind of the West version of the Green Revolution to everywhere. We can adopt it to different places and be much more sustainable, much more productive, and much more environmentally sensible. So, for example, to lift the yield of maize around the world would really not require very much additional nutrients. For example, a small, very small addition of nutrients, 20, 10, and 10 kilograms of nitrogen, phosphorus, and potassium, would be a huge increase in yield in Eastern Europe, parts of Mexico, and across Africa. This is about 1/10 of the nutrients provided to the typical European farm. This could be done with manures, it could be done with legumes, it could be done with synthetic fertilizers, whichever approach you like. It definitely could have a boost in yields and food security. And we could close the yield gap altogether with fairly reasonable additions of additional nutrients, soil amendments, and water. So the approach of closing the yield gaps could, in the last 20 years, raising the yield ceilings gave us 28% more food, and it's diminishing. closing the yield gaps from the lowest performers up to the highest could give us maybe 50 to 60% more food, much more, right where we need it, and a much more sustainable approach, because this kind of intensification could benefit a lot the crops that we have today with very little additions of nutrients and water. This leads to the third kind of recommendation we made about the resource efficiency of agriculture. We know that in most green revolution industrialized agriculture, we use an enormous amount of water and nitrogen and phosphorus and chemicals to grow our crops, but we could be a lot more efficient about it. For example, this is the amount of irrigation water being used on the planet today. The darker the blue is the more water being used in irrigation. So we see, the areas of irrigation around the world in India, China, the Middle East, the United States, a little bit of Mediterranean Europe. But that's not all that interesting, how much water is being used. We can look instead at water productivity. So we're looking at the kind of water productivity for cropland. I think another speaker will be talking about this for livestock in a minute. So this is going to be quite interesting, but on average, it takes a little less than 1 liter of water for irrigation to produce 1 calorie of plant material. That's a huge variation, though. It's not just 1 everywhere. It turns out that in some places like Israel, it's much less than 1, and in northwestern India and Pakistan and Iraq, for example, it's much more than 1. It's closer to 20 or 30. There's about 2 orders of magnitude difference in the efficiency of growing food with irrigation between the best irrigation systems and the worst. 100-fold difference, at least, probably more. So could we improve the efficiency of irrigation? Can we take the worst performers and make them a little bit better? Either saving water or growing more food, or maybe both. So there are huge opportunities here for efficiency improvements in water, but also for nutrients. This is looking at how much nitrogen is applied around the world, and then we can look at how much nitrogen is applied per ton of food that is grown. Kind of, what are you getting for the amount of fertilizer you're using? Well, interestingly, even though Africa, for example, uses very little fertilizer, they grow very few crops still, so the relative efficiency is somewhere in the middle. The United States is sort of in the middle. That's interesting. They're both comparable, but with very different farming systems. But it turns out India and northern China are the worst, least inefficient farms in terms of nitrogen productivity. India is interesting because there's huge subsidies in India for urea-based, not ammonia-based, but urea-based nitrogen fertilizers, and they're imbalanced with other nutrients. They have all this nitrogen, but they are typically lacking potassium. So crops are stressed by potassium, but oversupplied nitrogen just due to subsidies. So there are probably targets and opportunities here to be vastly more efficient. And it turns out about 40% of the excess nitrogen in the world's agriculture happens on only 10% of the world's farms. So in terms of water pollution, but maybe more importantly, nitrous oxide, an important greenhouse gas, there are huge opportunities to target regions here, here, and maybe here to dramatically lower nitrogen emissions into the atmosphere. So again, very big variations in the efficiency of how much food we get per unit inputs of water and nutrients, and that gives us a lot of opportunities to improve efficiencies and greenhouse gas emissions and water pollution and water withdrawals, and so on. Finally, the 2 recommendations that usually get us into the most trouble, as you can imagine, are saying, well, wait a minute. If we close the yield gaps and we maybe raise the yield ceilings, and we move efficiencies and so on, we still haven't doubled the amount of food in the world. We can't get to 100% increase. So maybe we have to question whether we can even do that, and do we want to double the world's global food throughput, or maybe we should look a little bit at diets and maybe at food waste, not just increasing the supply, but mitigating the demand. So we looked at those 2 issues also, and one of the things that's quite scary is how little food is actually food, right? This map looks at all of the world's cropland and asks what fraction of those crops are intended for human consumption. So the red places you can see here are between 80, 90, 100%. Those are places that grow basically exclusively human food. So we have China, India, most of Africa. They're growing food. The Mediterranean countries as well, for example, are growing food. You get to the green and especially the blue places, you're growing something that is not intended for direct human consumption. Animal feed, mostly, and biofuels. Now, animal feed, yes, that is going into an animal. That animal then maybe produces milk, which becomes dairy products, or maybe becomes meat, which we can eat, but with very much less energy and protein and calories than the original plants did. It's just physics, but there's a lot of inefficiency in animal grain-fed agriculture. So we look at this, and I was just in Lund the other day giving a talk, going, "Oh, interesting. Skåne seems to have one of the lowest food production efficiencies in the world. I better double check that data. I didn't think about that until I flew here." But then we look in the Midwestern U.S. near where we live, and it's only about 20% of those crops, those corn and soybeans and other things, are ever going to go into a human diet. Most of it does not. But you look globally, and it turns out that 60% of the world's crop production is human food. 40% is not. 40% of that, you break it down, it's roughly 35% is animal feed, and about 5% is biofuels. And the 5% is growing very quickly. So we have 40% of the world food system to maybe think about a little bit and to change. Interestingly, it turns out another 30 to 40% of all the food we have in the world is also wasted along the supply chains. In rich countries, mostly in the consumer end of the chain, in restaurants, in our homes and cafeterias, but in poor countries, it tends to be in the farmer end of the system where they can't get crops to market without spoilage or pest. So we have a lot of opportunities to think about diet and food waste. So we did this kind of interesting little analysis. This is not published yet. Emily Cassidy is working on this right now in our group. This wasn't exactly in our Nature paper, but you can see that what we did here. We basically said, what if, a very hypothetical scenario, but what if everyone were vegetarian, or we were vegetarians mostly, and the meat that we did eat were only from grass-fed grazing systems. We didn't divert grain into meat, where we lose 90 to 95% of its energy content, which is typical in most grain-fed beef operations. So we basically become mostly vegetarians, not entirely. We don't use food crops for biofuels anymore, and we figure out how to get rid of most of the world's food waste. Okay, very hypothetical, but kind of the best case scenario of how changing diets and changing food waste could feed the world. So what we did is we took every place in the world and we asked how much does it grow and turn that into calories, and we divided it into, imagine everyone in the world only ate 2,000 calories a day, which is a good diet. Americans eat more than that. We shouldn't, but we do. Europeans are getting to move that way as well. So this basically is how many people could be fed off of every hectare of land. The red areas are around 15, some of them are closer to 20, going off the scale here. But we see China, India, Western Europe, the United States. These are the places that are feeding the world, right? And you add this up and it's about 9 or 10 billion people could possibly be fed this way. Well, that's pretty good. Well, this is the possible food supply. Now keep your eye on Europe and the United States. See those nice, deep red colors of 15 to 20? I'm going to show you what happens when we actually have the real food system, including meat, including biofuels, including waste. So I look kind of near where I live, for example, over here in the US. Let's click and see where it is now. That's what we actually do in terms of feeding the world. Like Iowa, for example, a state near the where I live in Minnesota, that's a big corn-producing state. It dropped from 18 to 4. So instead of 18 people being fed per hectare, we feed 4 out of the net food system of that system. And actually some people near where I live get very angry at me when I point out that, yes, Iowa feeds about the same number of people per hectare as this part of Nigeria. American farmers aren't used to hearing that. Yes, we grow a lot of crop, but then we waste most of it. We don't turn it into food. We turn it into biofuels and hamburgers. Western Europe isn't doing that much better, frankly. It turns out China and India and Indonesia are feeding more people per acre than the Europeans and the Americans because of how we use these crops. If we add all this together, it's quite astonishing. We could feed another 50% more people in the world today by changing our diets. We could add another 30% possibly through changing food waste and improving that. So if you do the mathematics of all this, it's pretty simple. You can add up 50% here and another 30% there. Taking these 5 steps together, increasing the supply, improving efficiencies and environmental performance, and reducing the inefficient demand sides, We can double the world's delivery of nutrition easily by 2050 if we take all 5 of these steps together, and we can more than cut in half the environmental damages of agriculture. So the good news is that the physics and the biology of the planet tell us that yes, you can deliver more calories and nutrition to the world very easily while simultaneously reducing by a huge amount the environmental damages of agriculture. So this is a good news situation. But then people always ask me, well, what about climate change? This is one of the big uncertainties, along with emerging disease. Climate change will undoubtedly disrupt agriculture. I think maybe less than we expect, though. This is one of our scenarios of looking what would happen due to climate change if only climate change were happening in the world. If the only thing to happen in the next 40 years were to be climate change, by 2050, this is what might happen to yield changes in maize, for example, at least according to our estimates. Maybe 20 to 30% yield hits in some places, increases in others, though on net about a 10% drop in maize yield around the world. But it's increasing in the north, decreasing in the south, kind of like you would expect. The biggest issue is more water than it is temperature. Well, okay, that's one scenario, but the world is not going to just sit still and wait for climate change to happen. If we were to project increases in yields and closing yield gaps, what could be done on the technology side alongside climate change, this is what happens to yields. In fact, most of the world's yields are overwhelmingly increasing. Even the places that were decreasing a lot due to climate change in Africa, management changes could be far bigger than that, about 100% improvement in yields compared to a 20% decrease. So we get about an 80% net increase. So yes, climate change is important, but rarely in the world is only one thing changing. And yes, you still see a lot of problems here, but I guess the point here is that technology, policy, changes in how we farm and governance and so on have tremendous possibilities, if we're smart about them, to help us adapt to climate change, or hopefully to mitigate it altogether. I'm not dismissing climate change, but it's, don't do it as an experiment in a test tube where nothing else is going on. We will change far more than the climate will in the next 40 years when it comes to agriculture, and those two will have to come together in an interesting way where we deal with them at the same time. So I think we need to look at this in a more nuanced and broader perspective than we have before. Well, to wrap up, we have to look forward in this food system to how do we meet the demands of humanity, a growing number of people, a growing consumption of calories and meat around the world, and huge concerns about respecting the planetary boundaries of the Earth system. These are huge challenges, and we're going to have to find multiple solutions deployed at the same time. As you might have noticed in our presentation so far, there's no single solution to the challenges for food security and the environment. We came up with 5 that you had to, at a minimum, use all of them to get to the solutions we need. And we only looked at 5. There are many, many more that could be deployed. Interestingly, the ideas we talked about, too, were kind of agnostic about whether something was organic or conventional or local or global. It didn't really matter. Those kind of social labels on food have very little to do with how the Earth system works or how a food system delivers its calories to the world. So we argue pretty strenuously that, in fact, we have to move beyond just a simple label that says organic is better than conventional, or conventional is better than organic. I think we would argue that it would be, well, it depends. It depends where you are and what your goals are. Maybe we should measure the outcomes and performance of agriculture in terms of what is the human benefit of nutrition, calories, and so on, divided by its environmental damages in terms of water, carbon, nutrients, and biodiversity. Both organic and conventional have good attributes. Maybe we could bring them together and have the best of both in a new kind of third approach to agriculture. Local food is very good in some ways, but it's not a silver bullet to climate change or other solutions, and sometimes it uses more resources than global food. So why do we use local when that's best and global food when that's best? And instead of separating our solutions into one or the other, we're arguing we need to bring them all together if we're going to have a chance of solving these problems. And in doing so, I like to talk about, maybe we need just a whole reinvention of what we call agriculture anyway. And when we think about agriculture that actually respects the entire needs of the entire planet, that all of humanity's food security and living within the boundaries of our planet's environment, maybe we should move beyond kind of agriculture of the first 10,000 years of human history and invent an agriculture for the next 10,000 years that is farming for the whole planet, or maybe something we might call something like terraculture, farming for the future and farming for our planet into the next 10 millennia. Well, at the end of the day, this is what this is all about, and I'm really looking forward to hearing more conversations and discussion about this. How will we feed the world and sustain the planet? I would posit again that this may be the single biggest challenge we face in the 21st century, alongside other grand challenges like climate change, like emerging diseases, like dealing with poverty and so on. But this is kind of the central crux of all of them, will be how do we deal with our most basic of resources and human needs, food and land. And we absolutely have to get it right because we don't have any other choice. So with that, say thank you very much, and I think we have a little bit of time for questions. And so thank you very much for the chance to be here today, and I look forward to any comments you may have. Thank you.